welcome to your first topic in artificial intelligence. This topic will deal with search agent or planning agents. So far we have been talking about what we call reflex agents. These are agents that use a mapping from states to actions. In other words, reflex agent has a lookup table and they know what to do according to the states. Goal-based agents operate differently, but instead of having this predefined list of states to actions, the goal-based agents will have to find the solution for the problem. Just to put things back in context, I'm going to start first by drawing the level of intelligence. So that's level or intelligence level. On this side, we're going to put agents with high level of intelligence. On this side, we're going to put agents with low level of intelligence, right? So we could put our reflex agents at this level. So reflex agents are just agents that don't have any intelligence. They just have a lookup table. They look what to do according to kind of dictionary or a lookup table. All right. So reflex agents are considered as one of the lowest level of intelligence. We're going today to introduce what we call state-based agents. State-based agents, and it turned out that actually search algorithms or search agents are one of the categories of state-based agents. Okay, so I'm going to, as we go in this course, fill this axis with more and more intelligent agent as we see more and more topics in artificial intelligence. So what are goal-based agents? These are agents that work toward a goal, just like the name indicates. These are agents that consider the impact of actions on future states, which means that their job is to identify the actions or the action or series of actions that lead to the goal. In AI, this is formalized as a search through possible set of solutions. So in general, the search space of the possible solutions is large enough to prevent from putting this information or these solutions into a lookup table, and hence reflex agent won't be effective in this case. We need more of a goal-based agent that knows how to search through the possibilities and get the best solutions to the goal. To illustrate what goal-based agents do, let's take a couple toy examples. The first one is a maze. We all played with mazes. So for example, in this maze, we're trying to figure out a way to go from a starting point S here to a goal G in the middle of the maze. All right, so there are different ways we could do it. One possible way is to go, let's say, this way to the right, and then another one to the right, and then to the left, and then go to the left, and then keep going, search for a possibility to reach this point in the middle of the maze, and then I'm actually getting stuck here. So I could try other alternatives. So maybe let me try to go from the left and then go in this way, and then here again I'm stuck and there's no way I could get to the point, to the goal in the middle. So let me try. Last possibility is let's try the first path, but maybe change a little bit direction once we get closer to the goal. So maybe instead of going to the left here, let me go to the right. Nope, didn't work. A last one. Hopefully this will be a nice tentative, a successful one. So here I'm going to the left, and maybe maybe move it here, and then here, and then here. Got it. Okay, so the blue path was the blue is the success. The blue is a success path that leads us actually to the goal. All right, so what did I do? I just explored my search space to find one possibility, one path that led me to the goal. So what search agents do in general is something similar. They would actually explore the search space to find a path between the start and the goal of the search problem. Another toy example is called the 8-queen problem. So probably you played with that. So you have a chessboard on which we want to place 8 queens so that no queen is attacking another one. So how do queens attack another one? If they are placed on the same line, either horizontally, vertically, or diagonally. So this is an example, successful example, in which you put the 8 queens, such as no one is killing the other one or attacking the other one. So if I put one queen here, then this one will attack it, and it won't work. So this is a successful state that this is a goal state, right? A goal, what we call the goal state, in which actually we reach the point where we were able to put 8 queens on the chessboard. Let's think first about how we can count the number of possibilities or the size of the search space. So we have here 8 times 8 cells or positions on the chessboard, which makes 64 possibilities to put the first queen. So the first queen could be put in any of the 64 positions. The second queen will be put into 64 minus 1, since we already placed one queen, which will be leading us to 63 possible solutions, possibility to put the second queen, and so on and so forth. We're going to go down until 57 because we only have 8 queens. This represents a search space of 1.8 times 10 to the 14 possible solutions to put the queens on the chessboard. That's huge. This is all possible sequences on which we could put the 8 queens. Some of them are successful, some of them are not. And the idea of a goal-based agent is to find one successful possibility to put the queens on the chessboard. Problem solving as a search problem can be defined through 1, defining what's the goal to achieve, and 2, formulating the problem. These are 2 important aspects to tackle if you want to design a goal-based or search-based agent. So I would like to emphasize a subtlety here, which is that solving the problem is actually a 2-stage process. First, we need to search mentally or offline by exploring the set of several possibilities. And then we execute the plan or the solution found. So if you remember in the maze example, I did write the different paths that would lead from the start to the goal, but I could also do that mentally or offline, and then once I found a successful solution, I would execute it. So it's similarly, a goal-based agent won't really try and go ahead and try different possibilities and then go back to the start and start over. It will do the calculations mentally, and once it found, suppose it's a robot, once it found the successful solutions to go from point A to B, then it will execute it by moving effectively to that position. So we need to execute the solution found once we have explored and found a solution that leads us to the goal. Okay, so the problem formulation is in general done as follows. First of all, we need to identify what is our initial state, the state in which the agent starts. I was the agent when I did the maze. I started when I was in the lower circle of the maze. What are the states? These are all states reachable from the initial state by any sequence of actions. It's also called the state space. So there are different states as you are planning on how to move in the maze, for example, or where to put your queen. You are creating new states that actually change from the initial state to other kinds of possibilities. So this is called the state space. The actions are the possible actions available to the agent. For example, I could go ahead, go right, left on the maze. I could also put the queen on the top left corner or the bottom right corner, and so on and so forth. So I'm doing actions that will actually change a state from one case to another one. So actions are possible actions available to the agents. At the state S, actions of S will represent all possible actions that could be executed in the state. So this is called the action space. So here we're going to talk about action space and state space to define the different states of the problem and the different actions of the problem given each state. We also define what we call a transition model. This helps us actually describe of what each action does, which means that what are the resultant actions from being in the state S and applying some actions A. We also define what we call a goal test. This actually determines if a given state is a goal state or not. So we're going to have this kind of test that tell us whether we reached what we wanted to achieve or not. Finally, we define the last element is called the path cost. It's a function that actually assigns a numeric cost to a path with respect to some performance measure. It doesn't always exist, but whenever we have a performance measure we want to reach the goal, we are going to apply this function to know how much this is costing us. It could be a solutions, but there may be other solutions, and we want to see how much each of the solutions costs.